Look up at the night sky and try to imagine a place so remote that no matter how many times you gazed up at the stars, you'll never see it. Even if you could see incredibly far, through the dusty clouds of our galaxy and beyond the reach of our most powerful telescopes, you'd still be utterly lost. That's because we exist in a vast, interconnected structure made up of hundreds of thousands of galaxies, all held together by a scaffolding of dark matter. We call this the cosmic web. In the beginning, there was nothing, just a singularity, a point of infinite density and temperature. Then came the Big Bang, and the rapid expansion of space-time known as inflation. As the universe began to cool, energy started to condense into particles, and those particles into the first luminous objects, stars and galaxies. But how did these massive structures turn into a giant spiderweb? For the answer, we need to go back to the very beginning. In the first fractions of a second after the Big Bang, the universe was filled with a primordial soup of elementary particles. Most were identical, but some were slightly different. They had a tiny variation in their masses, a property we call asymmetry. Physicists have long been puzzled by this, because the laws of nature as we know them treat these particles as identical. How did they begin to differ? One theory proposes that the answer lies in the quantum realm, specifically in the behavior of empty space. According to quantum mechanics, even a vacuum is really a froth of ephemeral particles that pop in and out of existence. Some of these virtual particles have a tiny chance of becoming real when they interact with other particles. So as the universe expanded and cooled, the symmetry breaking between the elementary particles would have been established through interactions with virtual particles born of empty space. But we'll have to wait for the next generation of experiments to confirm this. Meanwhile, another story was just beginning. One that would sculpt the universe on the largest scales and dictate where galaxies would form. Matter in the early universe was not evenly distributed. There were slight variations in density, places where matter was slightly more bunched up. These fluctuations, smaller than a quantum, were the seeds from which the cosmic web would grow. In the second chapter, we'll learn how the cosmic web grew from these tiny seeds. But first, let's zoom out to get our bearings. We live on Earth, which is part of the Milky Way, a spiral galaxy around 30,000 light-years across. Our galaxy is surrounded by smaller galaxies and clusters of galaxies, all grouped together in a structure called the local supercluster. Within this supercluster, there are around 100 groups of galaxies, each containing several smaller galaxies. And each of these groups is embedded in an enormous expanse of near-empty space. To understand the large-scale structure of the universe, astronomers map the distribution of galaxies and group them into clusters. Galaxies in a cluster often have similar properties such as size, shape, and velocity. And these groupings of similar galaxies are known as the nodes of the cosmic web. Where do they come from? The answer goes back to the initial density fluctuations and the role of gravity. Gravity pulls matter together. So in regions where matter was slightly more dense, gravity caused even more matter to clump together, until over time, entire galaxies formed. And that process didn't happen just once. It happened everywhere, creating a network of galaxies linked together by filaments of glowing matter. But these structures weren't inevitable. Their formation required a unique set of conditions in the early universe. For example, the universe had to expand fast enough to keep the galaxies from clumping together too much. And it had to expand slow enough to allow structures to form at all. Indeed, the web would not exist if the rate of expansion was faster than a critical value. When scientists analyze the web, they look for signs of these early conditions imprinted in its structure. In the third chapter, we'll explore what the cosmic web tells us about our origins. But first, let's zoom in again. Each galaxy in the web is made of hundreds of trillions of stars, each containing a solar system much like ours. Stars form in giant clouds of gas and dust known as nebulae, and every once in a while, one of these stellar nurseries gives birth to a planetary system with planets and life. All around us, then, are the raw materials for worlds like Earth. But are there other Earths out there? And if so, how common are they? The number of Earth-like planets in the Milky Way could range from a few billion to many trillions. Astronomers can estimate this by studying stars similar to our Sun and looking for planets in their habitable zone, the region around a star where conditions might be suitable for liquid water to exist. Although we haven't yet found definitive evidence of extraterrestrial life, some scientists think that life as we know it might be fairly common. Others argue that there's something special about our solar system, or that we in the midst of a cosmic fluke. The idea that we're alone is unsettling, but it's also hard to prove or disprove. The sheer size of the cosmic web makes finding other life extremely challenging, even if it's relatively common. Despite this, the cosmic web holds clues about our origins. By mapping its structure, astronomers hope to piece together how the universe evolved from the Big Bang to the present day and predict how it will evolve in the future. In fact, the web structure tells us that the universe is not infinite, but finite and flat, meaning that it extends infinitely in one direction and curves infinitely in the other. In the sixth and final chapter, we'll learn why the cosmic web may hold the key to understanding dark matter. But first, let's step back again and consider the truly mind-boggling scale of everything we've discussed. We began with the Big Bang, the event that birthed the universe. Then we looked at the small-scale processes that gave rise to galaxies, stars, and planets. Then we zoomed out to consider the large-scale structure of the universe, and finally, our place within it. The universe is so vast that it seems impossible to comprehend. But as we've seen, we can make sense of its structure by studying the distribution of galaxies and mapping the threads of the cosmic web. By doing so, we've uncovered an astonishingly beautiful structure that is both familiar and strange, comforting and terrifying. Now let's zoom out one last time. The universe is so big that no matter how far we travel, we can never see the whole thing. The cosmic web is all around us, stretching in every direction, connecting us to the other galaxies in the local supercluster. Yet at the same time, it's nowhere. Can't see it directly, only the galaxies that populate it. By studying the web, we can learn more about ourselves and our place in the universe. We can study the conditions that led to the formation of the first galaxies, stars, and planets. And we can learn more about the mysterious dark matter that holds the web together. By understanding the web, we can better understand ourselves. And who knows? We may even find other worlds like Earth, or perhaps worlds that are even more special. The more we learn about the cosmic web, the more we uncover about the universe and our place in it. And that knowledge is one of the most humbling and exhilarating experiences we can have. In the vast expanse of space, there exists a network so intricate and colossal that it defies human comprehension. A cosmic tapestry woven from the threads of galaxies, spanning billions of light years. It is a silent testament to the relentless forces of gravity and the eternal dance of matter and energy. Today, let us embark on a celestial journey to unveil the secrets of this grand design and unravel the enigma of the cosmic web. But before we dive into this cosmic wonder, we have a request. If you find our content intriguing and informative, please take a moment to support us by liking this video. Your support means the world to us and inspires us to continue exploring the depths of our universe. The story of the cosmic web begins with the birth of the universe itself. In the fiery crucible of the Big Bang, all matter and energy were compressed into an infinitesimal point. As the universe expanded, it carried with it the echoes of this primordial chaos, fluctuations in density and temperature. These minute variations, magnified by the relentless march of time, became the seeds of the cosmic web. As the universe evolved, gravity took center stage, orchestrating a cosmic ballet that would span billions of years. It drew matter from the vast emptiness into dense knots, stretching and twisting the threads of dark matter into an ethereal web. But what is dark matter? It is a mysterious substance that makes up a significant portion of the universe's mass, yet remains invisible to our telescopes. Dark matter's presence is inferred through its gravitational effects on galaxies, but its true nature continues to elude scientists. It is this elusive substance that forms the backbone of the cosmic web. Normal matter, on the other hand, is the familiar stuff that makes up stars, planets, and even ourselves. Stars' colossal nuclear furnaces emerged as the first luminous beacons in the cosmic darkness. They provided the light that illuminated the web, revealing its majestic structure. Filaments and sheets. The cosmic web is not a random scattering of galaxies. It is an intricate network of interconnected structures. Galaxies, the building blocks of this web, are grouped together in vast clusters and superclusters. These clusters and superclusters are not evenly distributed throughout the universe, but follow the contours of the web's filaments and sheets. Filaments are long, thin threads of galaxies extending over hundreds of millions of light years. They are the pathways along which galaxies move and interact. Sheets are larger, more extensive structures that form the planes of the cosmic web. Within these sheets, galaxy clusters are grouped together like beads on a string. Voids. Interspersed between the rich tapestries of filaments and sheets are vast empty regions known as voids. These cosmic deserts can stretch for billions of light years, containing only a sparse scattering of galaxies. Despite their apparent emptiness, voids play a crucial role in the evolution of the cosmic web. They provide the canvas upon which new structures can emerge and evolve. The walls of the web are adorned with the grandest structures in the universe. The largest known objects by far, the superclusters. These immense groupings of galaxies extend over thousands of millions of light years and contain hundreds of smaller clusters. Some of the most prominent superclusters in the night sky include the Laniakea supercluster, of which our Milky Way is a part, and the Shapley supercluster, one of the closest superclusters to us. At the heart of this cosmic ballet, our Milky Way dances gracefully. Its position within the web is not a random one. Like all galaxies, it is drawn to the web's structure. Moving along its filaments and influenced by the gravitational pull of its neighbors, the Great Attractor. At the core of the web, hidden within the recesses of the Virgo supercluster, lies an enigmatic region known as the Great Attractor. This massive gravitational anomaly has a profound influence on the motion of galaxies within 100 million light-years of Earth. Its presence is a testament to the web's immense power, shaping the destinies of entire galaxies. But the cosmic web is not a static structure. It is a dynamic, evolving entity. Galaxies within the web constantly interact with each other, influencing each other's shape and evolution. Mergers and collisions are not uncommon, reshaping the web's intricate tapestry. The web itself is not immutable. New structures emerge while others fade away. The cosmic dance is eternal, driven by the relentless forces of gravity. Mapping the web. The study of the cosmic web has revolutionized our understanding of the universe. Astronomers use sophisticated computer simulations to map its vast expanse. Tracing the web's filaments and superclusters, X-ray telescopes reveal the web's hidden structure, unveiling the hot gas that permeates the filaments and delineates the boundaries of voids. By charting the web's intricate pathways, scientists hope to unravel the secrets of galaxy formation and the evolution of the universe itself. Dark energy. The discovery of the cosmic web has led to profound implications for cosmology. The web's large-scale structure provides evidence against the idea of a static universe. It reveals that the universe is expanding, and that expansion is accelerating due to a mysterious force known as dark energy. Dark energy, which makes up nearly 3/4 of the universe's mass and energy content, counteracts gravity, driving the accelerated expansion. Understanding dark energy and its influence on the cosmic web is one of the greatest challenges in modern cosmology. In recent years, the study of the cosmic web has unveiled some intriguing mysteries. One such enigma is the web's surprising homogeneity, despite the universe's vastness. The distribution of galaxies and the properties of the web's filaments and voids appear remarkably similar on scales both large and small. This homogeneity suggests that the web's structure is not merely a product of chance, but may reflect deeper underlying principles. Another fascinating aspect of the cosmic web is its multi-scale nature. The web's structure is self-similar, meaning that similar patterns and features can be found at different scales. From the smallest filaments to the largest superclusters, this self-similarity has puzzled astronomers and has led to speculation about the role of chaos and deterministic processes in the universe. Moreover, the cosmic web has provided insights into the behavior of dark matter. As the web's structure evolved over billions of years, it has left behind a distorted gravitational lensing effect around massive galaxy clusters. By studying these distortions, astronomers have been able to probe the distribution and properties of dark matter, shedding light on this elusive substance's role in the universe. Looking ahead, the future of cosmic web research is filled with exciting possibilities. The James Webb Space Telescope, with its advanced infrared capabilities, will revolutionize our understanding of the web's early evolution. By peering deep into space, it will unveil the faint light from some of the universe's first galaxies and shed light on the web's formation in the cosmos. Web researchers are also pushing the boundaries of computer simulations, creating more detailed and accurate models of the web's evolution. These simulations, coupled with data from telescopes and missions like the Sloan Digital Sky Survey and the Dark Energy Survey, are providing an increasingly precise map of the web's structure. Moreover, the web's connection to dark energy is a major focus of current research. By analyzing the web's large-scale properties, astronomers are refining measurements of dark energy and its impact on the universe's expansion. The hope is that, by unraveling the mysteries of dark energy, they will unlock a deeper understanding of the web's evolution and the ultimate fate of the cosmos. The cosmic web is not merely a scientific curiosity. It is a profound reflection of the order and complexity that emerges from seemingly simple beginnings. The universe, with all its immensity and grandeur, is bound together by the delicate threads of a cosmic tapestry. As we continue to explore the depths of space, let us marvel at the intricate beauty of the cosmic web and the elegant laws of physics that govern its existence. For within its vast expanse lie not only the secrets of the universe's evolution, but also a testament to the boundless curiosity and ingenuity of the human spirit. As far back as humans have looked into the night sky, we've seen a vast, seemingly endless expanse of stars. And as far as we've explored the universe, we've found a vast, seemingly empty expanse of space. For most of history, people believed the universe must be infinite. It would be hard to imagine a beginning to the universe if there was no end to it. In the last century or so, we learned there is a beginning and an end. And in the last several decades, we've even begun to see that the universe isn't empty. There's a lot going on out there. We're realizing that the universe is finite. It's only 94 billion light-years across. It also appears to be flat. Space doesn't curve on the largest scales, and we can see almost all of it. But just because the universe is small and flat doesn't mean it's completely uniform. When astronomers began to catalog all the places we've seen things in space, they realized there were patterns. There's a huge amount of stuff between the Earth and the edge of the universe, and it's not distributed evenly. The universe looks like a cosmic web. Space has large empty areas called voids, separated by thin filaments and sheets of galaxies. And the biggest of these structures seem to stretch all the way to the edge of the observable universe. The first big one we found was the Sloan Great Wall. It was detected in 2003 when scientists analyzed data gathered by the Sloan Digital Sky Survey during its first 2 years of operation. SDSS scanned a significant portion of the northern sky and collected information about more than 240,000 galaxies. When researchers sorted through them and plotted their locations, they noticed something strange. There didn't seem to be any patterns to the positions of the galaxies. At least not at first. Then they started looking at the data differently. They grouped galaxies together, making walls of different sizes until they found the best fit. And then they found it, a giant wall-shaped structure so vast it defied explanation. It was made of around 8,000 galaxy clusters totaling 500,000 galaxies grouped together over a span of 640 million light-years. This was the Sloan Great Wall. It was difficult for researchers to explain because the Sloan Great Wall contradicted the main idea behind the standard model of cosmology, which says that the universe is homogeneous. It means the universe should look basically the same from any vantage point. Homogeneity is also a key prediction of Einstein's theory of general relativity. His theory of gravity says that on large enough scales, the universe should be smooth and featureless. The Sloan Great Wall clearly wasn't featureless. So astronomers tried to come up with an explanation. Maybe they had missed something when collecting the data. Maybe the galaxies weren't actually grouped together but only appeared to be due to random chance. Or maybe the universe really isn't homogeneous. They decided it was probably best to err on the side of caution and assume they had done everything correctly, so they moved on. But now they needed to explain how such a gigantic structure could exist. One of the prevailing ideas at the time was that the early universe underwent a brief period of exponential expansion known as inflation. Inflationary theory says that, in the first tiny fraction of a second after the Big Bang, the universe expanded incredibly quickly before slowing down to the rate of expansion we see today. But if inflation had occurred, it should have smoothed out any large-scale structure in the universe. The Sloan Great Wall was too big to be a simple fluctuation in the matter distribution caused by quantum effects in the early universe. It also didn't match up with the predictions of any models that took inflation into account. The conclusion was that the early universe must have been more complicated than anyone thought. The Sloan Great Wall showed astronomers that even though the universe is largely uniform, there are some rare regions that have slightly different properties. Since then, surveys of deeper and deeper regions of space have revealed that the Sloan Great Wall is just one of many similar structures scattered throughout the universe. Together with other scientists, they form a giant network of galaxy clusters and filaments. This is the cosmic web. There's one structure in particular that dwarfs the Sloan Great Wall in both size and importance. It's Laniakea. The word Laniakea is Hawaiian for immense heaven, and it's appropriate because the structure is unimaginably large. It includes our home galaxy, the Milky Way, along with hundreds of thousands of other galaxies. Researchers determined the size and shape of Laniakea in 2014. When they published a study mapping the motion of galaxies within 520 million light-years of Earth, the team identified 8,000 groups of galaxies and then used computer simulations to work out how each of those groups and individual galaxies were moving. They found that the Milky Way, along with the Andromeda Galaxy and the Virgo cluster of galaxies, are all bound together by gravity in a massive structure stretching over 520 million light-years. It's a supercluster, and we're part of it. In fact, scientists estimate that there are about 100,000 galaxies in Laniakea, including the Milky Way, each containing trillions of stars. Laniakea isn't a neat, orderly grouping of galaxies. It's not a sphere or a cube or any kind of geometric solid. It's more like a flat pancake with filaments extending outward from it. Those filaments contain galaxy clusters, grouped together in a web-like structure. Laniakea sits at the center of a cosmic web supercluster. And like the Sloan Great Wall, it presents a problem for cosmologists who believe in the standard model. As far as they can tell, it shouldn't exist. It's just way too big. Some physicists have suggested that structures like Laniakea and the Sloan Great Wall could help solve one of the biggest problems in modern physics. The trouble is dark energy. According to the standard model, the universe should be slowing down as it expands, but experiments show it's actually speeding up. The only way to account for that is to hypothesize a force called dark energy. It would counteract gravity and speed up the expansion of the universe. Some physicists speculate that there might not be dark energy. Instead, the universe might be inhospitable to structure on the largest scales. Because of dark energy, structures like Laniakea and the Sloan Great Wall might be the result of a temporary fluke in the distribution of matter. They will eventually be torn apart by the accelerating expansion of the universe. If true, that would mean the universe does eventually become homogeneous, and the standard model would be saved. Of course, it's possible that the universe doesn't operate like that. Maybe there are genuinely huge numbers of superclusters like Laniakea sprinkled throughout the universe. If so, dark energy would have to somehow leave those structures alone. That might not be possible, though. Maybe there are some interaction between dark energy and normal matter that causes the structures to fall apart as the universe expands. Scientists are still trying to figure it out. So far, they haven't been able to confirm the existence of even bigger structures. They've suspected that there might be since 2013. When researchers studying the distribution of gamma ray bursts across the sky reported finding evidence of an immense wall-shaped structure spanning 10 billion light-years. Gamma ray bursts are the brightest explosions in the universe, releasing more energy in a few seconds than the sun will over its entire lifespan. They occurred during the formation of neutron stars and black holes. And because they're so bright, they allow astronomers to see really far away. In fact, studying gamma ray bursts is one of the best ways to probe the most distant parts of the universe. In their study, researchers gathered data from more than 2,500 gamma ray bursts and analyzed the distribution of their host galaxies. What they found was a wall-shaped structure so large it stretched halfway across the observable universe. The sheer size of the structure, dubbed the Hercules corona Borealis' Great Wall, raised questions about whether it was really a wall. Some scientists argued that the distribution of gamma ray bursts was just a statistical fluke, a combination of random chance and the uneven distribution of matter in the universe. The host galaxies of Gamma bursts might not be randomly distributed, but the bursts themselves should be. That would mean the Hercules corona borealis' Great Wall is only an apparent structure and not a real one. Others have argued that it is real and that it points to flaws in the standard model. But there hasn't been enough data to reach a conclusion since the study was published. Other teams of astronomers have searched for the Hercules corona borealis Great Wall and haven't found it. But those searches haven't been able to cover the whole thing. They've only checked parts of it. The reason it's been so difficult to find is that the Hercules corona borealis' Great Wall is more than 3 times the size of anything else like it. If it exists, it would push our understanding of the universe in some very interesting directions. It would imply that there's a lot more matter in the universe than we think. It would show that on the largest scales, the universe doesn't follow the rules we think it does. We'll continue to search the skies for it and for other gargantuan cosmic structures. The more we learn, the better we understand how the web of the universe evolved from the Big Bang to the present day. And maybe someday soon we'll know if the Hercules corona borealis Great Wall is real or just a statistical fluke. Maybe the size of the universe isn't infinite after all, but finite. But not only that, the size of the universe seems to be stable. That means that as far as we can tell, there's nothing beyond the edge of the universe. This would imply that the universe is really a sphere. We live in the middle of it. And if that's true, that makes us very special. Or maybe it doesn't. Maybe the universe is just the way it is. Imagine you're standing in a forest, see trees around you, perhaps a stream or a clearing. But as you step back, you realize that the woods stretch farther than you can see. Your position becomes meaningless. There is no center. This realization is humbling. You're part of something vaster and more profound than yourself. And if you stand at the edge of a cliff and gaze down at the earth, the same idea strikes you. You are just here for a brief moment, a visitor on a tiny rock sailing through an endless sea of stars. We humans love to think of ourselves as special, and there is good reason for it. Our existence depends on the fact that our planet has the conditions needed for life as we know it. But when we contemplate the vastness of space, our significance shrinks. We are just one speck in a mind-bogglingly huge cosmos. In this corner of the universe, we find ourselves in a cosmic forest of sorts. Space is filled with a network of enormous galaxy clusters linked together by filaments of galaxies. These filaments form a vast web stretching across billions of light years, and it's still growing. Here on Earth, we see this cosmic web all around us, above us, below us, and in every direction. We are adrift in a cosmic sea of galaxies. The cosmic web is more than just a pretty picture. It's the key to understanding the evolution of our universe. It reveals how matter is distributed across the cosmos, how galaxies grow, and how the universe itself is expanding. But the web also poses profound questions. What made it in the first place? What does it tell us about the fate of the universe? And are we at its center? It's me. Welcome to Cosmos. The web of galaxies was first proposed in the 1970s based on the distribution of galaxies in the nearby universe. Since then, we've mapped the web across billions of light years. The web consists of immense galaxy clusters, forming the peaks and filaments of the structure. Between them are vast, nearly empty voids. The web grows as the universe expands. Galaxies move away from each other as space itself stretches. Over billions of years, these structures have evolved through a delicate balance between gravity, which pulls matter together, and the expansion of space, which pushes it apart. Our home galaxy, the Milky Way, sits near the center of the local supercluster, a group of about 50 galaxy clusters held together by gravity. Most of the Milky Way's neighbors are in a relatively small region called the local group, within the local supercluster. We can see a few of the filaments of the cosmic web. One, called the Great Rift, extends over 300 million light-years and includes the Andromeda Galaxy. Other filaments reach even farther into the depths of space, where the universe becomes too dim and sparse to map. The cosmic web represents a deep truth about our universe. On large scales, it is mostly empty. The familiar constellations and fuzzy patches of galaxies and nebulae that fill our night sky represent. It's just a tiny part of the cosmic web, but that's not all. While our universe may appear chaotic, The positions of galaxies follow a simple rule. Their distribution mirrors the pattern of peaks and valleys in a topographical map. This is not a coincidence. The topography of the universe is the result of physical processes governed by the laws of nature. We can observe similar patterns in sand dunes on Earth, the ripples in a pond, and even the swirls of smoke rising from a fire. These patterns arise because natural systems tend to organize themselves into stable, low-energy configurations. The same is true for the cosmic web. Gravity pulls matter together, creating clumps and filaments. Meanwhile, the fabric of space expands, pushing things apart. The result is a dynamic and ever-changing structure that reflects the underlying physics of our universe. In this way, the cosmic web acts like a palimpsest, preserving clues about the history of the universe and revealing the fundamental forces that shape it. By studying this structure, we hope to uncover the secrets of how galaxies form and evolve, how matter is distributed throughout the cosmos, and even how the universe began. But to truly understand the cosmic web, we need to explore its most mysterious feature, the voids. The largest known void is called the Boat's Void, named after the constellation it occupies. With a diameter of 650 million light-years, it could fit 250,000 Milky Ways in a line. The sheer emptiness of the boozoid is difficult to comprehend. It contains only a handful of galaxies, making up just 0.03% of the matter in the region. It's not just empty space. The void contains a thin gas, the leftover heat from the Big Bang. So even though there are a few galaxies, there is still plenty to explore. By studying the light that passes through the void, scientists can learn about the chemical activity occurring in the tenuous gas. And because voids expand faster than denser regions of space, they offer a unique opportunity to study dark energy. Dark energy is the mysterious force that is accelerating the expansion of the universe. It makes up about 2/3 of all the energy in the cosmos, but its nature remains unknown. Voids are particularly sensitive to the effects of dark energy because they expand faster than other regions of space. By measuring the rate at which voids expand, scientists can better understand the properties of dark energy. Despite our growing knowledge of the cosmic web, much remains unknown. One major puzzle is the origin of the web's structure. How did the filaments and clusters of galaxies form in the first place? Computer simulations suggest that the seeds of the web were planted in the tiny fluctuations in the early universe, which then grew under the influence of gravity. However, the details of this process are still being investigated. Another mystery concerns the distribution of matter in the web. According to our best measurements, the universe is made up of equal amounts of matter and energy. But we can only account for about 5% of the matter in the universe. The rest is missing. Some scientists speculate that much of this missing matter resides in the filaments of the web, in a form that is difficult to detect. Others suggest that the problem may lie in our current understanding of physics, hinting at the possibility that new particles or forces may be at play. Finally, we still don't fully understand the largest structures in the web, the superclusters. These immense groups of galaxies pose a particular challenge because they are so massive that they distort the fabric of space-time around them. Understanding how superclusters form and evolve could help us unlock some of the deepest mysteries of the universe. But even as we continue to explore the unknown aspects of the cosmic web, we can appreciate the profound implications of this structure. The web is a testament to the order and complexity that arises from simple physical laws. It reveals the interconnectedness of all things in the universe and reminds us of our place in the grand scheme of existence. When we look up at the night sky, we see not just a random scattering of stars, but a vast and intricate structure that reaches in every direction. The cosmic web is a reminder that the universe never ceases to amaze. And as we continue to explore its depths, we can be sure that many more wonders await discovery. This video was made possible by our incredible community of patrons. Just like the cosmic web, our community is a vast and intricate structure. Each patron is a vital part of this network, working together to make incredible things happen. Without your support, we wouldn't be able to make videos like this, so thank you. And if you want to be a part of our community, you can get started at our website. Until next time, keep looking up. And remember, the universe is full of magic. All you have to do is find it. When I embarked on my journey to film this episode, I didn't realize the extent to which the cosmic web would captivate me. It's not just a fascinating structure in space, but a reflection of the deeper truths about our existence. It made me wonder, how do we as humans find our place in this vast web of galaxies? Are we merely a random occurrence or an inevitable outcome of the laws of physics? As I delved deeper into this topic, I came across an interesting perspective. Some believe that the very structure of the cosmic web is a testament to the purposefulness of the universe. They see the emergence of galaxies and clusters as a sign of an inherent order in the cosmos, a tendency towards complexity and organization. This view challenges the traditional scientific perspective that sees the universe as a clockwork mechanism driven by deterministic laws. Instead, it suggests that there may be a deeper intelligence at play, guiding the evolution of the cosmos towards greater complexity and eventually towards life itself. Of course, this idea is highly controversial and goes against the prevailing scientific consensus. But as I continue to explore the mysteries of the universe, I find myself drawn to the idea that there may be more to existence than just blind chance. The cosmic web may not just be a beautiful structure in space, but a roadmap of our existence, pointing towards our ultimate destiny. We often think of the vastness of space as a featureless vacuum. But when viewed from above, our universe is more like a spider's web than a black hole. It's an intricate network of galaxies strung together in a cosmic dance as old as time itself. It's called the cosmic web. And when we speak of galaxies, walls, and voids stretching billions of light years, it can feel impossibly distant, as though humanity is too small to matter in such a vast architecture. But the cosmic web is not just an abstract structure out there. It is also the environment in which Earth and life itself exist. To understand this, we must trace our address in the cosmos. The Milky Way's positioner planet orbits a modest star, the Sun, one of roughly 100 billion stars in the Milky Way galaxy. The Milky Way itself is a barred spiral, stretching about 100,000 light-years across. But the Milky Way does not exist in isolation. It is part of a small, gravitationally bound group of galaxies known as the Local Group, which includes the Andromeda Galaxy and several dozen smaller dwarfs. Zoom out further, and the Local Group belongs to the Virgo Cluster, a dense region containing thousands of galaxies. And the Virgo cluster itself sits inside the much larger supercluster we call Laniakea. In other words, Earth's cosmic address can be written like this. Earth gives solar system, gives Milky Way gives, Local Group gives Virgo cluster, gives Laniakea supercluster, gives cosmic web. This nesting of structures mirrors the very way the web is built, small scales feeding into larger ones, all interconnected across the universe. The great attractor and our motion known of the most striking consequences of living in the cosmic web is that our galaxy, and therefore, Earth, is not standing still. Within Laniakea lies a gravitational anomaly known as the Great Attractor, a dense region pulling galaxies toward it. The Milky Way, along with our Local Group, is racing through space at roughly 600 kilometers per second relative to the cosmic microwave background. This means that even as Earth orbits the Sun and the Sun orbits the galaxy, our galaxy itself is flowing through the cosmic web, like a leaf drifting along an invisible current of gravity. The web we inhabit is not just a static backdrop to life on Earth. It is a dynamic structure that shapes our existence in ways both obvious and subtle. Let's begin with the obvious. The cosmic web is the reason why Earth has neighbors. We share this cosmic address with countless other celestial objects, each potentially harboring its own forms of life. Understanding the web helps us navigate this galactic neighborhood, predict potential collisions, and explore the diverse environments found in our cosmic backyard. But the cosmic web's influence extends far beyond our immediate surroundings. Its structure, with its rich filaments and vast voids, plays a critical role in shaping the conditions for life as we know it. Consider galaxy formation. Stars and galaxies form along the filaments of the web. These filaments act as cosmic highways, guiding the flow of gas and dust that coalesce into new stellar systems. Without these filaments, the universe might be dotted with isolated stars, rather than the grand spiral arms and clusters we observe. Moreover, the web influences the chemical composition of galaxies. As stars live and die, they enrich the surrounding space with heavier elements. These elements forged in the hearts of dying stars are then incorporated into new stars and planets, contributing to the very building blocks of life. Earth, with its abundance of heavy elements, owes its existence to the recycling of material across the cosmic web. Furthermore, the web's structure affects the stability of galaxies. Our Milky Way resides in a relatively quiet region of the cosmic web, sheltered from the violent activity occurring in the denser, more crowded areas of galaxy clusters. This relative peace has allowed life to flourish on Earth, without being constantly disrupted by cataclysmic events that might have otherwise wiped out life as we know it. But what if we take a step back and consider the web's influence on the web itself? Could the large-scale structure of the universe play a role in creating conditions suitable for life? Some scientists speculate that the emergence of life might not be a purely local phenomenon. Instead, it could be intrinsically linked to our location within the cosmic web. Proponents of the anthropic perspective argue that if life is a rare occurrence in the universe, our existence suggests that the universe must be somehow tuned to allow for life to emerge. Our location within a filament of the cosmic web, they argue, might be a crucial factor. Filaments provide the ideal environment for galaxies to form and evolve, offering the right balance of stability, resources, and isolation. They serve as cosmic nurseries where stars and planetary systems are born, providing the building blocks for life to arise. On the other hand, the voids of the cosmic web are too empty, and the dense galaxy clusters are too chaotic. Thus, our place in the cosmic web may not be merely coincidental. It may be a necessary condition for life to flourish. From galaxies to maps. Mapping the web now, let us shift our perspective from the web. Influence on our lives to humanity's journey in mapping this cosmic structure. The story of the cosmic web is intrinsically linked to the remarkable story of human discovery. Our understanding of the universe's structure has been shaped by centuries of observation, innovation, and the relentless human spirit of exploration. The foundations of modern cosmology were laid by astronomers like Galileo Galilei, who made groundbreaking observations with his telescope, revealing the wonders of the Milky Way. As more precise instruments came into use, scientists began to peer beyond our galaxy. The early 20th century saw a revolution in our understanding of the universe with the advent of general relativity by Albert Einstein and the inclusion of the expanding universe by Edwin Hubble. These theories provided the framework to view the universe as a dynamic, ever-changing entity. However, it was only in the late 20th century that we started to piece together the large-scale structure of the universe. The Sloan Digital Sky Survey, launched in 2000, was a monumental effort to map the positions of galaxies. This ambitious project captured a three-dimensional map of the universe, laying bare the immense web-like structure that stretches across billions of light-years. By analyzing the distribution of galaxies, scientists revealed the filamentary nature of the universe, a vast network of galaxy clusters and superclusters connected by cosmic filaments. Yet the story doesn't end there. More recent surveys, like the Aerosita, a Russian-led international collaboration, have delved even deeper. Focusing on the distribution of galaxies and clusters in the universe, this mission has provided an X-ray perspective on the cosmic web, allowing scientists to study the distribution of hot gas that permeates the universe's skeleton. Mapping the cosmic web has not only deepened our understanding of the universe's structure, but has also raised profound questions. For instance, the web's immense size and complex structure have led scientists to ponder whether the universe is infinite or if it has boundaries. Furthermore, the web's evolution over time has become a subject of intense study. By observing how the web changes, scientists hope to gain insights into the nature of dark energy, the mysterious force accelerating the expansion of the universe. As our technology advances, we stand on the brink of even more exciting discoveries. Gravitational wave astronomy, a new frontier in astrophysics, promises to shed light on the dynamics of the cosmic web. By detecting ripples in space-time caused by the movement of massive objects, scientists will be able to probe the web's structure and evolution in unprecedented detail. In conclusion, our place in the cosmic web is more significant than it may initially appear. We are not merely observers of the universe. We are integral parts of this vast, intricate structure. From the formation of galaxies to the distribution of elements, the web shapes the conditions that make life possible. And our efforts to map and understand this web have not only expanded our scientific knowledge, but have also revealed the profound interconnectedness of our existence. As we continue to explore the universe, we do so knowing that we are tracing our cosmic roots, seeking to understand the very fabric of the reality we call home. For most of human history, the universe appeared flat, simple, and limited. The stars were fixed to the night sky, the planets wandered among them. Galaxies, when they were eventually discovered, seemed like isolated islands of light. But as telescopes improved, astronomers began to ask a bold question. What does the universe look like on its largest scales? The answer required a revolution in how we map the cosmos. In this video, we'll explore how astronomers peered deep into the heart of the universe, charted a web of galaxies across billions of light years, and created a map of the cosmos like no other. The key to understanding how our cosmic cartographers measured the fabric of space lies in something called redshift. Imagine a cosmic ruler with miles of string attached to it. You hold one end and pull out the string to measure distances. But how do you know when you get to exactly 1 mile? You need markers along the string, things to indicate how much string you've let out. In the case of the universe, those markers are distant galaxies, and their light gives us clues about their distance. Light waves come in many colors, which correspond to different wavelengths. Blue light has shorter wavelengths, while red light has longer ones. If a galaxy is moving away from us, the light waves it emits are stretched, shifting the color toward the red end of the spectrum. The farther the galaxy is away, and the faster it's receding, the greater the stretch and the deeper the redshift. The amount of redshift tells us how fast the galaxy is going away from us, and because the universe is expanding, it also tells us how far away it is. Knowing a galaxy's distance and its position on the sky gives us enough information to plot it in 3 dimensions. From there, we can create maps of the distribution of galaxies across the universe. But this approach only became possible in the late 20th century after several crucial technologies came together. Large telescopes capable of collecting enough light from dim galaxies, sensitive detectors to analyze the spectrum of that light, and powerful computers to crunch the numbers. The first major redshift survey was the CFA redshift survey in the 1980s and 90s. When all this data was plotted on a map, it showed an unexpected feature: voids. Huge regions almost completely empty of galaxies. The CFA survey revealed that the universe is not a simple, featureless expanse. It's a complex, foam-like landscape of galaxy clusters connected by filamentary structures and punctuated by immense voids. After the success of the CFA survey, a new project was launched in 2000 with even grander ambitions. The Sloan Digital Sky Survey, or SDSS, would map a huge slice of the sky using a dedicated 2.5-meter telescope in New Mexico. Over 5 years, SDSS collected data on more than 100,000 galaxies and quasars and stitched them together to create a 3D map of the universe. The results were published in 2003 and shocked the astronomical community. Walls, filaments, and sheets of galaxies leaped off the screen. The most famous of these is the Sloan Great Wall, a vast expanse of galaxies spanning 420 million light-years. Other structures like the Hercules corona Borealis' Great Wall are even larger. The map also revealed enormous cavities of emptiness, some up to 650 million light-years across. These voids are so big they could fit hundreds of thousands of galaxies like our Milky Way. What makes the SDSS maps so striking is the sense of depth. Unlike traditional star charts, they show how far away objects are from Earth. The trick is color. Distant galaxies are shown in red and blue. Closer ones, closer still, are white. With this system, you can tell how close or far away an object is just by looking at its color. This makes the maps more than just pretty pictures. They're a window into the evolution of the universe. By comparing nearby and distant galaxies, we can see how structures change over billions of years. And thanks to computer simulations, we can compare those changes to our models of how the universe works. 2 projects in particular have advanced our understanding of the cosmic web. The first is the Millennium Simulation, a massive project led by the Max Planck Institute for Astrophysics in Garching, Germany. Using supercomputers, the team simulated the evolution of the universe over 13.7 billion years. The simulation included 10 billion particles representing both dark matter and visible matter, primarily hydrogen. By watching the positions of these particles, the researchers could track the development of the cosmic web from the smallest scales to the largest. Another simulation, Illustris, took a slightly different approach. Instead of modeling dark matter particles, Illustris focused on gas and how it moved through the simulated universe. The result is a stunning visualization of galaxy formation, showing how gas clouds collapse, turn into stars, and shape the evolution of galaxies. These simulations are not just useful for understanding how the web evolved, they're also helping us figure out how it will evolve in the future. As the universe expands, the cosmic web will change in response to dark energy, the mysterious force that is accelerating the expansion. Scientists hope to use the past as a guide to predict how the web will change in the next few billion years. To make our maps of the cosmic web even better, we need even more data. And that's where the next generation of redshift surveys comes in. The 2DF Galaxy Redshift Survey in the UK surveyed over 220,000 galaxies in the early 2000s. More recently, the Baryon Oscillation Spectroscopic Survey, or BOSS, extended the range of SDSS to include fainter, more distant galaxies. By studying these distant galaxies, astronomers can look back in time and study how the cosmic web evolved in the past. BOSS also helped researchers test a key prediction of the Big Bang Theory, the standard model of cosmology. The theory says that matter and energy in the early universe were evenly distributed. But over time, variations in density grew through gravity to form the cosmic web we see today. This model predicts that the size of those variations should match what we see in the cosmic microwave background, the afterglow of the Big Bang. And amazingly, the data from SDSS and BOSS confirmed that prediction. But that's not all. Another experiment, the Wiggler's Dark Energy Survey in Australia, studied variations in the cosmic microwave background and found that they matched what we see in the distribution of galaxies. These results provided strong evidence that our understanding of the evolution of the universe is correct. Today, the most ambitious redshift survey ever undertaken is underway. The goal of DESI is to create the most detailed map of cosmic structure ever, covering 10 billion cubic light-years around Earth. This will allow scientists to measure how the cosmic web has changed since SDSS and improve tests of the standard model of cosmology. The sheer scale of the project is mind-boggling. DESI will collect data for 5 years, taking spectra of nearly 4,000 galaxies every night. All told, it will generate over 40 terabytes of data, equivalent to nearly 10 million digital photographs. It's a fittingly grand project for such a grand achievement. The DESI maps will be a crowning jewel of cosmic cartography, charting the vast landscape of galaxies and quasars in unprecedented detail. It is hard to overstate the significance of these maps. For the first time, we have a complete picture of the universe on the largest scales. We know how matter is distributed from one end of the observable universe to the other. This knowledge is allowing us to test our theories of cosmology, understand the evolution of galaxies, and search for the mysterious effects of dark energy and dark matter. Moreover, these maps are a testament to the power of the scientific method. Through careful observation, rigorous analysis, and theoretical modeling, we have learned to map the fabric of space-time. We've come a long way from the days when the night sky was seen as a flat, featureless dome. Today, we see it as a vast, intricate web stretching across billions of light-years. Our cosmic cartographers have done the seemingly impossible. They have mapped the skeleton of the universe. But this story doesn't end here. Space is big. Really, really big. In fact, it's so big that the idea of trying to wrap your mind around it feels practically impossible. It's like try to imagine a sphere that's 94 billion light-years in diameter. That's how big space is. Now imagine packing that sphere with trillions upon trillions of galaxies, each filled with trillions of stars, then spread that sphere out over 13.8 billion years. Your brain should hurt. And even still, that's just the space we can see. There is more space beyond that we can't unsee because light has had enough time to reach us yet. All this bigness makes it hard to get our bearings, to find our place in the cosmos. So naturally, scientists have come up with a way to map it, creating a three-dimensional atlas of the universe to help us better understand where we fit in. And in doing so, they found something incredible. A cosmic scaffold that stretches across billions of light-years and gives rise to everything we see. This is the cosmic web. When most people think of space, they picture an evenly distributed field of points of light. Maybe they're right. Maybe space is just a random assortment of galaxies strewn about, each independent of all the others. But maybe space is actually more like a sponge than a bowl of jelly beans. When you look closely at the distribution of galaxies, you see that they form filaments, sheets and clusters, separated by vast, mostly empty spaces. And when you plot the three-dimensional location of these structures, they form something that looks a bit like a spider web, hence the name. The cosmic web doesn't look quite like the spider silk you might imagine. It's more like a spider web after a strong wind blows through it. The filaments stretch and distort, connecting into a huge network that spans billions of light years. But it's there if you know where to look. In some places, the filaments converge into dense concentrations of galaxies, which scientists call clusters. And in others, the filaments are so tenuous that they're virtually impossible to see. The cosmic web has both large-scale features and small ones, but we'll start with the biggest. The biggest feature in the web is the Great Wall of Hercules' corona Borealis, structure 600 million light-years across containing hundreds of galaxy clusters. And even bigger than that, there's the Hercules corona Borealis Great Wall, a gargantuan wall of galaxies so large that no single human has ever been able to view it entirely. It would take nearly 2 hours of staring in one direction to see it all. The thing about these gigantic walls is that they don't look like anything on Earth. You could compare them to the Great Wall of China or Hadrian's Wall. Because they too big, you need to go bigger. The biggest wall you can imagine, the biggest wall that humans have ever built, is nothing compared to the walls of galaxies in deep space. You need to use different categories of comparison. It's like trying to explain the length of a guitar string to someone who's never heard of music before. They won't have the context to understand the concept of length. Instead, you'd have to show them the string vibrating to produce sound. Likewise, to understand the cosmic web, we have to start with the sounds that make it up. The sounds of the cosmic web are gravity and dark energy. Gravity pulls matter together, and dark energy pushes it apart. For billions of years, these forces were roughly in balance, allowing matter to clump together into stars and planets, and eventually black holes, into entire galaxies and galaxy clusters. More recently, dark energy has started to win the fight. As it pulls away from everything else in the universe, causing the cosmic web to expand at an accelerating rate, scientists have known that dark energy exists, but they're still struggling to figure out exactly what it is. The prevailing hypothesis is that it's a property of space itself, kind of like background radiation. Just as ripples spread outward from a pebble dropped in a pond, dark energy permeates all of space, pushing galaxies apart from one another. This means that in the future, the filaments of the web will become thinner, and the clusters of galaxies within them will drift farther apart. Eventually, dark energy will push everything out of contact with one another. And at that point, the cosmic web will fall apart, dissolving into an unobservable darkness. But until that happens, gravity will hold things together. Gravity brings things closer. It links galaxy clusters into filaments, pulls gas and dust into new stars. It forms planetary systems and shapes black holes. Basically, gravity is the architect of the universe, designing every building and room and hall. The cosmic web is its masterpiece. It's a structure that emerges from the smallest particles to the largest galaxy clusters, guided by the same fundamental rules. Everywhere you look, you see evidence of this. If you zoom in on a region of the cosmic web, you see smaller webs forming inside of them. Zoom in again, and you see smaller webs within those. Keep zooming in, and you see the same thing happening everywhere. From the largest scales to the smallest, the web is self-similar. No matter how far you zoom in or out, you see the same basic structure everywhere. The idea of infinite complexity emerging from simple rules is pretty common in nature. Take a snowflake, for example. It starts as a single water molecule. Then as it drifts through the atmosphere, more molecules attach to the first one, forming a lattice of ice crystals. Pretty soon, that one molecule has turned into an intricate six-sided structure. The snowflake has emerged from a simple set of rules, and so has the cosmic web. At its core, the web is a product of the rules of physics. It's a graph of where matter falls in the universe. To create this graph, you have to specify 4 pieces of information for each dot. First, you note the type of object that it represents, whether it's a galaxy cluster, or something else. Next, you record the brightness of the object, which tells you how much mass it has. After that, you add the object's location on the sky, specifying its right ascension and declination, which are just fancy ways of saying left to right and up to down. Finally, you add the distance to that object, telling you how far away it is. With all 4 pieces of information recorded, you can map the universe. If you do it right, you can find the cosmic web. You can think of it like the social web. Every person in the world is a node in a gigantic network, connected to everyone else by roads and wires and satellites. Some connections are stronger than others. Your best friends are more tightly linked to you than your acquaintances. But overall, the social web has a similar structure to the cosmic web. Most people are connected to a few other people, which creates a filament. A few people have lots of connections, forming densely packed clusters of overlapping filaments. And in between the clusters are mostly empty regions where few people live. The social web isn't as pretty as the cosmic web, though. No one has created a simulation of it, and honestly, it's a little creepy to think about. The good news is that scientists have made maps of the cosmic web. Some of the maps look like crumpled paper. Others look like wrinkled fabric. Still others look like a chaotic jumble of lines. The maps aren't perfectly accurate representations of the universe, simplifications based on the data that scientists have available. But they're still useful tools for studying the cosmic web. In fact, the Sloan Digital Sky Survey used 10 years of observations to create the largest 3D map of the web, charting more than 9 million points. It's so big that if you tried to print it out, the full-color version would take up 10 billion sheets of paper. Fortunately, you don't need to print it out to appreciate its beauty. NASA has released a series of videos showing how you can fly through the web, soaring through its nodes and along its filaments. But remember, the cosmic web is always changing. Gravity and dark energy are continuously tugging it into new shapes. In a few billion years, the map will look totally different. So if you want to experience the web right now, before it changes, you should check out NASA's videos. They're the closest thing we have to time travel. And thank you for watching this Sea Show video.